Thanks again for the introduction and good afternoon again. We are dealing more or less all with the same kind of topic, which is fatigue of miniaturized lattice specimens. The work that has been done by Raffaele before, presented before, as well as the first presentation of today. However, I decided to not work. No. See? Okay. I intentionally decided to keep exactly the same introduction, but under a different perspective. I said that we have structural integrity issues concerning lattice metal AM materials. And these are mainly associated, of course, to the mechanical properties. These properties can be seen as a function of three main factors, which are the choice of the base material, the choice of the geometrical architecture of the lattice that we're dealing with, as well as the choice of the fabrication process. This gives the mechanical behavior as well as the defect sensitivity that we have within a component. Usually, when we are dealing with fabrication process of metal AM, most of the time, at least for the, let's say, most ready technology within the industries, we are dealing with laser powder bed fusion. But even within laser powder bed fusion, we have different, let's say, sub-technologies. For instance, how we are working on our laser and how the emission of a laser is done. It can be, for instance, a pulsed wave or a continuous wave. Within this, we can understand that the overall melt pool dynamics that we have, if we use a pulsed wave strategy with respect to a continuous wave strategy, will totally change. This will affect the morphological properties and consequently will affect the mechanical properties and will assess the structural integrity of the components. So within this presentation, we decided to work still with TI-64 miniaturized specimens, and in particular with the continuous and the pulsed wave laser powder bed fusion with two industrially optimized set of parameters. What does this mean? This basically means that we are trying to balancing the productivity, so the print speed, as well as the dimensional accuracy, so the defect sensitivity that we have inside the component, trying to avoid like more than 48 hours printing jobs, as well as to achieve good results for mechanical validation. But usually when we have this kind of balance, which is in between two counterintuitive requirements, we usually neglect the fatigue reliability and how the fatigue behavior of this component is. So the question of this work is to try to assess the fatigue behavior of these components according to these two industrially optimized set of parameters for pulsed wave and continuous wave components. The specimen design is exactly the same. 90 degrees, 45 and 15 degrees are the building orientations that we are dealing with. And the pulsed and continuous wave processes, as said, are industrially optimized, but we are trying to keep some parameters in common in order to have a fair comparison. These parameters are, for instance, the layer thickness, which has been kept at 60 micrometers, as well as the feedstock powder, which is exactly the same, and also to have comparable energy density per track width, which is for pulsed wave and continuous wave reported here. So given this, we decided to start with our, let's say, usual approach of definition of the cross-section of our components. I will not go in detail of this since it has been already described in two presentations before. And these are mainly the principal results that we have in between the pulsed wave and continuous wave according to the three different building orientation from 50 to 90 degrees. What you can clearly see here is that there are some statistical significance differences in between the continuous and the pulsed wave. Basically, the pulsed wave specimen report a higher load-bearing area with respect to the continuous wave specimens. And in general, the continuous wave laser powder bed fusion specimen are below the nominal values, while the pulsed wave are usually above these nominal values of 670 micrometers. It's important for us to have an idea of how the cross-sections are in each specimen because we want to basically nullify the differences of cross sections within our SN curves. Indeed, if I would have used the nominal cross section here, we would have way larger differences in between the pulsed and the continuous wave laser powder bed fusion specimen. Technically speaking, if this would have been the only difference, we would have a perfect match of the curves. Of course, there isn't, because the melt pool dynamics change and the morphology of the specimens changes, not only the cross-section. And indeed, you can clearly see that for this test that has been done in a fully reversible fatigue regime at R equal to -1, we do have clear differences with respect in between the continuous wave and the pulsed wave laser powder bed fusion specimens. In particular, we have that pulsed wave reports better fatigue behavior with respect to continuous wave laser powder bed fusion specimens. This is already, it's probably more visible here in the trends that we have at fixed numbers of cycles. And you can clearly see that this is particularly true for lower building orientations at 45 and 15, while at 90 degrees, but I will discuss about this later, we have a perfect match at 10 power 5 cycles, but this match is not anymore valid at 10 power 6 and 10 power 7 cycles, respecting the trend of the other two building orientations. So, as I was saying, like the mechanical properties and the fatigue strength of the component is dependent on these three main areas. But here we are keeping the base material fixed, is the same feedstock powder. The same architecture is the same type of specimen. So we are just changing the fabrication process. So probably this difference is related to what the fabrication process brings to the overall final component in terms of surface defects, porosity, and microstructure, which affects the overall fatigue strength. For this reason, we decided to investigate step by step all these aspects, starting from the surface roughness analysis. This analysis has been done dividing into two skins the component, which are the upper skin and the lower skin of the component, and according to the three different building orientations, as well as the two different processes. Here you can clearly see that for the case of 45 and 15 degrees, we do have clear differences in surface roughness, with a higher surface roughness for the continuous wave with respect to the pulsed wave laser powder bed fusion specimens, particularly for the RV values, which are the most used and employed for fatigue assessment. However, if we check the 90-degree specimens, we do not have any kind of statistical significance, meaning that probably we can describe only partially by the surface roughness effect these differences and these scatters in between the fatigue behavior of the two different processes. So we decided to step on and checking the porosity. We perform porosity analysis as has been done for the 369 components. So basically slicing in different parts several components. And what we've seen is that in the case of 15 and 45 degrees, we more or less have an equivalence. While in the case of 90 degrees, it's clearly visible that there is a higher concentration of pores in between the contour and the edge of the component for the case of pulsed wave laser powder bed fusion, which are the ones that are reporting the better fatigue resistance in comparison with the continuous wave. So these results, it seems to be counterintuitive with respect to what we are actually obtaining. So meaning that mostly probable porosity in this case is not taking part, or is not relevant at least, for the fatigue downgrading of pulsed wave laser powder bed fusion, continuous wave laser powder bed fusion components. Given this, and if we check again these trends, as I was mentioning before, there is a perfect match at 10 power 5 cycles, while there is a discrepancy at 10 power 6 and 10 power 7 cycles. But this is not related to surface roughness, neither to porosity. So the next step to check is associated to the microstructure, if there is any kind of microstructural differences due to the different process. And this is what we actually try to check with ABSD analysis of 90-degree specimens. We can clearly see that there is no specific difference in the alpha grain, which have a comparable size and length, but we do have differences in the prior beta grains of this kind of specimens in which the pulsed wave reports way larger prior beta grains with respect to the continuous wave laser powder bed fusion struts, which have instead smaller and more complex structures of these prior beta grains. The answer, the question is, does this affect fatigue? Are the prior beta grains affecting explaining the differences in fatigue? And the answer was given by literature, by a really nice work of the group of Sanjid, crystal plasticity work published in 2023 in the International Journal of Plasticity, which basically states that the larger the beta grains are, the more statistical, the less statistical probable is that we will have a failure due to plastic strain localization at the grain boundaries, which leads basically to having the larger beta grains, a delay crack initiation, and so higher fatigue strength. So the smaller the beta grains are, the more grain boundaries we have, the more plastic localization, strain plastic localization we have. While conversely, the larger the beta grains are, the less statistically possible is that we have this kind of concentrations that can lead to microstructural failure. But this is also, can also explain this work, the cyclic effect that we do have, in which we have a perfect match at 10 power 5 cycles, while we do not have it at 10 power 6 and 10 power 7 cycles. And this is that this kind of effect is mainly related to high cycle fatigue, and in particular to initiation controlled mode. So given this, we probably are able to explain these discrepancies and these trends by the microstructure and by the role of prior beta grains. So just to summarize, we've seen that if we keep two industrially relevant and optimized sets of parameters for two different technologies within the laser powder bed fusion, so the continuous wave and the pulsed wave, we do have differences, and these kind of differences are mainly associated to the melt pool dynamics, which alters the overall geometry of the component. Particularly, depending on the building orientation we do have for 4515, we usually have lower surface roughness for the pulsed wave with respect to the continuous wave, which explains the greater fatigue behavior. While for the 90 degrees is due to microstructural changes that we do have while we are printing and cooling the specimens. So, of course, we are at a preliminary stage of this work. We need to extend the analysis of EBFD to the other orientations. And the final goal would be to develop some quantitative models which are able to account both for the microstructural as well as the surface defects effect within this kind of components. Again, thanking all the authors of this work and acknowledging the butterfly project of Professor Berto. Thank you very much. If you have any question, glad to answer.